I wanted to start this video off by saying this. You're doing an amazing job at preparing for your board exams. I know it's a really stressful time and I believe that you will get through it. In this video, what we're going to do is we're going to discuss an overview of the chapter Aldehydes, Ketones, and Carboxylic Acids, and the whole video is obviously going to be in English. And full disclosure, I did record this video in the year 2021. There has not been any change in terms of the syllabus, but the channel was much smaller then, and I think a lot of people will be benefited from this video at this point in time, and I hope you find this helpful. As always, definitely let me know if you have any questions, any concerns, or if you have any doubts with respect to this chapter or any other chapter. Well, I hope you enjoy it.
Let's begin with the syllabus for the chapter aldehydes, ketones, and carboxylic acids. You do not have you have the entire chapter. There's not going to be any deletion of syllabus. So we start with learning about the nomenclature of aldehydes and ketones, followed by nature of the carbonyl group and methods of preparation, physical chemical properties, and the mechanism of nucleophilic addition, as well as the reactivity of alpha hydrogen in aldehydes. So carboxylic acids, on the other hand, again, we'll be learning about nomenclature, the acidic nature of carboxylic acids, and the methods of preparation, physical and chemical properties, and uses. So generally, for any functional group that we've been learning from haloalkanes and haloarenes, that's the general rules that are followed. We start with nomenclature, we study about the nature of that particular compound, and then we talk about the various ways of preparation, the chemical physical properties, and if there's something unique in case of haloalkanes and haloarenes, you learned about nucleophilic substitution reactions and certain other unique reactions. So let's begin. Nomenclatures of aldehydes and ketones. We will be learning about common names as well as IUPAC names. So let's begin with common names. Generally, aldehydes and ketones are referred to by their common names itself. Like acetaldehyde is not called ethanaldehyde, but we just call it acetaldehyde. So the name for aldehydes is usually derived from the corresponding carboxylic acid. And carboxylic acids, their names are again derived from the source from which they are extracted from. And so that you'll again be learning when we talk about the nomenclature of carboxylic acids. Next, the substituents are going to be indicated by alpha, beta, gamma. So the alpha carbon is the one which is attached to the carbonyl carbon. The next one is going to be beta. After that, it's going to be gamma. So remember, the alpha position is at the it's the carbon which is attached to the carbonyl carbon. It's generally a little confusing. Sometimes people assume that this carbon is the alpha carbon. It is not. It's this one which is the alpha carbon atom. Next, in case of ketones, you have two alkyl or aryl groups which are bound, and their substituents are indicated by alpha, alpha dash, beta, beta dash, based on the carbon which you start. It starts from here, so this is going to be alpha. This will be alpha dash because you have two chains, because it's going to be in the. It has two alkyl groups attached to it. So when we talk about phenol which is attached, when you have an acyl group which is attached, we refer to it as a phenone. So this is acetophenone, and you have benzophenone because there are two benzene substitute. It has a benzene ring as well as a acyl group. Both are acyl, but one of them is referred to as a phenone. Next, we talk about IUPAC names. IUPAC names are very, very important. In grade 11, you had learned all about the basics of the IUPAC nomenclature. If you still find IUPAC names difficult, you can go back to that right now and just brush it up, because always remember IUPAC names. From what I've seen, that the compounds that you are asked to name these compounds. So it's better to have those basics thorough, and once you're thorough with the basics, then you should come on to, then automatically you don't even have to look at this. You'd be knowing all of that by now. So in case of aldehydes, the suffix is al. In ketones, it's on, and numbering will begin from the carbon of the aldehyde group. Whereas in ketone, it's going to be with respect to the number which has a lesser number. So basically, the CO of the ketone, the carbonyl has to get a lesser number. So it will be numbered accordingly. So for example, over here, ethanol, okay, yeah, 4-bromo 3-methyl heptanol. So the numbering would start from this carbon atom. So 1, 2, 3, 4, 4-bromo, 3-methyl heptanol, 7 carbon atoms. In ketones, however, you have it as, okay, where is that? Oh yeah, but this is again balanced. So in case of ketones, it's numbered in such a way that the position, the end nearer to the carbonyl carbon. The substituents will be prefixed as always, but they're arranged in their alphabetical order. So you have 4-bromo, 3-methyl heptanol. B is going, maybe in the alphabetical order, bromo comes before methyl. And in case of cyclic ketones, for example, this one, you have the carbonyl, the carbonyl carbon as number, and it is numbered as 1. And when the when you have an aldehyde attached, in this case, you name it as carbaldehyde. So this shows that this particular cycle has a aldehyde group attached to it. So the a cycloalkane is named. After that, you follow it with carbaldehyde. And benzene carbaldehyde is the simplest aromatic aldehyde, but we don't call it by the IUPAC name. We, however, refer to it as benzaldehyde. And the various substituents are referred to as the substituents of a benzaldehyde. One more important thing, when we talk about aldehydes and ketones in the same compound, the aldehyde is considered the principal functional group, and that's why it's as a suffix over here. Whereas ketone is going to be referred to as CO, which is not a principal functional group. I hope you remember the order of functional groups which you learned in grade 11. So here you have a table with common names as well as the IUPAC names. Go through them, try and basically name them, and you'll find it automatically easy to complete this particular, to understand IUPAC nomenclature. With that, we're done with the nomenclature of aldehydes and ketones. Structure of carbonyl groups. Hybridization. The carbon atom is sp2 hybridized. So it will form three sigma bonds, two of them with two alkyl groups or an alkyl and the hydrogen atom if it's an aldehyde or ketone. And the third sigma bond is going to be with the oxygen atom. It is also going to form a pi bond with the oxygen atom. So the valence electron is in the p orbital and it forms a pi bond. So the oxygen atom is going to have two non-bonding electrons, and the structure as such is going to be the three groups, that is the three sigma bonds are going to be in the same plane, whereas the pi cloud is going to be above and below, and it has a bond angle of 120 degrees. Now we know that oxygen is more electronegative than carbon. So oxygen atom has a tendency to pull the electrons towards itself, and that makes this double bond between the carbon and oxygen a polarized one. So the carbonyl carbon is going to act as a very good electrophile, which means it is electron loving, and it's also a Lewis acid. Whereas carbonyl oxygen, on the other hand, is going to act as a nucleophile because it's nucleus loving, because of its negative charge. Now, because of this negativity, because of this high amount of difference of electronegativity between carbon and oxygen, we know that there is going to be something called a dipole that is also observed. And this dipole moment, this dipole moment is also shown based on the resonance structures. So here you have the carbonyl. So here, this is one of the resonance structures, the normal thing that we see. And this shows the negative charge on the oxygen and the positive charge on the carbon, because this bond shifted to the oxygen atom because of its high electronegativity. Now, carbonyl compounds actually have a high dipole moment, and they are more polar than ethers. So with that, we're done with the structure of carbonyl groups. So carbon atom is sp2 hybridized, has three sigma bonds and one pi bond. The three sigma bonds are going to be in the same plane, whereas the pi cloud is going to be above and below. You have a bond angle of 120 degrees, and the carbon oxygen bond is, it's polarized because of the high electronegativity of the oxygen atom. Preparation of aldehydes and ketones. I've always found it easier to have a list of the reactions in each case, so that it's easier for us to recollect what the various methods of preparation or the chemical reactions are. So first of all, aldehydes. So we learn preparation of both aldehydes and ketones. Next is going to be just about aldehydes. The third is going to be about ketones. And look at these two. If you notice, you have acyl chlorides for both aldehydes and ketones. So there's going to be a change in the reaction conditions. Then here you have nitriles. Here also you have nitriles. And from hydrocarbons, actually, some of the reactions, or rather many reactions in this case, are going to be from benzenes or substituted benzenes. So there is a certain extent of similarity between these two. So the first is preparation of aldehydes as well as ketones, and this is going to be from alcohols. So the oxidation of alcohols, all these reactions have been taken from the previous chapter, alcohols, phenols, and ethers. So what happens is you have a reaction called as dehydrogenation taking place. So primary alcohol undergoes oxidation to give us an aldehyde. And based on the reaction conditions that we give, that is the oxidizing reagent that is used, we can stop the reaction at the aldehydic stage. And if it's a strong oxidizing agent, it will go directly to form a carboxylic acid. So when we have CrO3 as the oxidizing agent, we are getting the aldehyde. So primary alcohols will give aldehydes, whereas ketones, on the other hand, are formed from secondary alcohols. In this case also, we are using chromic anhydride as the reagent. Next is by hydrogenation of alcohol. So when you have the reaction with metals, primary and secondary alcohols undergo dehydrogenation. And like in the previous case, primary alcohols are forming an aldehyde, whereas a secondary alcohol is forming a ketone. Notice there is, to an extent, a lot of similarity between these two. Next is from hydrocarbons. The first one is by ozonolysis of alkenes. Now, this reaction is something you've learned in grade 11. So we have an alkene. It is going to undergo reaction with ozone to form ozonide. This ozonide is going to break to give us smaller molecules. And this particular compound is cleaved by using Zn in H2O. And this reaction is actually also used for identification of double bonds, and the products formed are aldehydes and and ketones. That's basically carbonyl compounds based on the kind of reactants which are being used. So here you had just a CH3CH double bond CH2. Now, if this H was again replaced by another CH3 group, then we got a ketone and an aldehyde. So we are alkene reacts with ozone, form ozonide, reacts with, in the presence of Zn and H2O, zinc and H2O, to form the smaller molecules which are aldehydes, or basically carbonyl compounds. Next is by hydration of alkynes. So as such, alkynes are insoluble in water. Now, when alkynes are warmed with mercuric sulfate and dilute sulfuric acid at 333 Kelvin, they form carbonyl compounds. So what are they doing? They're warming alkynes with mercuric sulfate and dilute sulfuric acid. And this is at 333 Kelvin. Now, in case of ethyne, it will give us acetaldehyde, whereas the other alkynes that exist will give us ketone. So here you see, you have the ethyne undergoing reaction in the presence of water, and then you have mercuric sulfate, and the H plus denotes dilute sulfuric acid. And this is leading to the formation of this particular product, which on isomerization forms ethanol. Whereas propyne is going to give us a ketone. Next, let's look at the various preparation. As I told you, here we are going to be studying about preparation of aldehydes and preparation of ketones separately. So since two of those reactions are common in both the cases, I decided to just put them as one table. And I love putting things in tables. So I put it as a table, and here it is. So first, let's look at the preparation of aldehydes from acyl chlorides. Now, Rosenmann's reduction involves the acyl chloride undergoing hydrogenation to form an aldehyde. Catalyst is palladium on barium sulfate. So here you have benzoyl chloride. It's undergoing hydrogenation in the presence of palladium on barium sulfate to give us benzaldehyde. Similarly, the same acyl chloride is reacting with dialkyl cadmium to give us ketone. Now, this dialkyl cadmium is prepared by reacting cadmium chloride with Grignard reagent. And if you remember, Grignard reagent was the one which we studied when we talk about haloalkanes and haloarenes. So do not learn these two as separate reactions. I mean, to an extent, it might help you remember these two as well. But it's all about being able to remember stuff. Next is from nitriles. So Stephen's reaction is for the synthesis of aldehydes. Notice you have two named reactions for aldehydes and none for ketones. So Stephen's reaction reacts a nitrile with stannous chloride and hydrochloric acid, and this gives us an imine. That on reaction with H3O plus is giving us an aldehyde. So that is the reaction put here. Okay, so nitrile stannous chloride in hydrochloric acid is giving us an imine, that is this particular compound, which in the presence of H3O plus is giving us an aldehyde. Nitrile can also react in the presence of dibal H, which is diisobutyl aluminium hydride, to give us an imine that again gives us an aldehyde. Here, if you notice, the two steps have just been concised to one. So 1 and 2, it shows that first this reaction takes place, then this one reaction takes place. One more important thing, the dibal H does not affect an alkene. This double bond does not get affected by the dibal H. Nitriles with Grignard reagent form an imine salt, which on further reaction in the presence of H3O plus give us ketone. So both the cases you have something called imine forming. In case of Stephens, it's just imine, whereas in case of for ketones, it is an imine salt. And that in the presence of H3O plus is giving us a ketone. This one that is from esters is only applicable to aldehydes. It's not for ketones. So esters are reacting with dibal H to give us an aldehyde. And this is the reaction given below. Next is preparation of aldehydes from hydrocarbons. Now, aromatic aldehydes are prepared by these methods. So the first one is oxidation of methyl benzene. So when you have methyl benzene like toluene, so these are going to get converted to benzoic acids. Now, the oxidation can be stopped at the aldehydic stage by using a weak oxidizing agent, and that's what we did in case of alcohols also. When we used a strong oxidizing agent, it converted directly to an acid, but we don't want that. We want the aldehyde, right? So we use a weaker oxidizing agent. So the first one is using chromyl chloride. So chromyl chloride, this particular reaction is also called as an ETARD reaction. Toluene reacts with chromyl chloride to give us this chromium complex, and that on reaction gives us benzaldehyde. So first, when you learn this reaction, always for all these reactions, just write it in this format so you remember at least like what the reaction contains. And then from there, I'm pretty sure you can write the names like toluene, benzaldehyde. The chromium complex is the only one. Chromium complex as well as the chromyl chloride are the only two formulae that you're going to have to learn as such. So simplify the way you learn chemistry always. So here toluene is reacting with chromyl chloride to give us a chromium complex, which on further reaction gives us benzaldehyde. Another way we do the same reaction is by using something called as chromic oxide. Now we have toluene or substituted toluenes, and they react with chromic oxide and acetic anhydride. And this leads to the formation of something called as benzylidene diacetate. And that corresponds, on hydrolysis with aqueous acid is giving us the corresponding benzaldehyde. And both these reactions involve chromium complexes. The first one is called as ETAR reaction. The next one is by side chain chlorination followed by hydrolysis. Now here you have toluene. It is reacting with, it's undergoing side chain chlorination, and that's giving us something called as benzyl chloride. And this on hydrolysis is giving us benzaldehyde. So this is actually the commercial method used for the preparation of benzaldehyde. So here you have toluene. It's undergoing chlorination by Cl2 and HMU. HMU shows that there's light involved, and it's leading to the formation of benzyl chloride. Benzyl chloride is the CH3. Two of the hydrogens have been replaced by chlorine atoms. And this is undergoing hydrolysis to give us benzaldehyde. And the last method is by Gattermann-Koch reaction. Now, Gattermann-Koch reaction involves benzene or its derivatives reacting with carbon monoxide and HCl. And this is in the presence of anhydrous AlCl3 or CuCl. So this reaction, benzene or its derivatives reacting with carbon monoxide and HCl in the presence of anhydrous aluminium chloride and CuCl. And this gives us benzaldehydes or substituted benzaldehyde based on the substitution of the benzene ring. The last one is the preparation of ketones from benzene or substituted benzenes, and this is Friedel-Crafts acylation reaction. Benzene or substituted benzene is reacting with acid chloride in the presence of anhydrous AlCl3 to give us corresponding ketone. And Friedel-Crafts acylation and alkylation reactions have been studied in detail when, or rather, you studied about it in your haloalkanes and haloarenes. So with that, we're done with the preparation of aldehydes and ketones. Easy, right? First, start with alcohols. Alcohols will undergo oxidation. Primary alcohol is going to give us an aldehyde. Secondary is going to give us a ketone. Dehydrogenation, it's passed over copper. And both of these aldehydes, both primary as well as secondary alcohol undergo dehydrogenation to give aldehydes and ketones respectively. Now, when we talk about hydrocarbons, we'll talk about ozonolysis of alkenes and from alkynes, hydration of the alkynes, and that is giving us respective aldehydes and ketones. It's only ethyne which gives us acetaldehyde. The remaining alkynes are giving us ketones. Now, when we talk about preparation of aldehydes and ketones together, we have it from alkyl chlorides and from nitriles, as well as from esters for aldehydes alone. Do not learn them separately and like confuse yourself, but learn them in the form of this comparison, and it will make things relatively easy. The next one is from hydrocarbons, preparation of aldehydes from hydrocarbons. And this is mainly used for aromatic aldehydes. So you have strong oxidizing agents, they will get converted directly to acid. So we use weak oxidizing agents like chromyl chloride and chromic oxide. And then we learned about the side chain chlorination, where toluene was converted to benzyl chloride, followed by hydrolysis to form benzaldehyde. And the last one is Gattermann-Koch reaction, where we took benzene or its derivatives, reacted with carbon monoxide and HCl in the presence of anhydrous AlCl3 and CuCl to form corresponding benzaldehydes or substituted benzaldehydes. Whereas the preparation of ketones from benzene or substituted benzenes was done by the Friedel-Crafts acylation. So you have acid chloride and the benzene or substituted benzene reacting in the presence of anhydrous AlCl3 for us to get the corresponding ketone. So here we've learned about we learned about four or five named reactions: Rosenman reduction, Stephen reaction, Etard reaction, Gattermann-Koch, as well as Friedel-Crafts acylation. With that, we're done with the preparation of aldehydes and ketones. Physical properties of aldehydes and ketones. First, we'll talk about state. At room temperature, gases, methanol, volatile liquid, ethanol. I actually added an extra T over there. Liquids or solids are going to be other aldehydes and ketones. Boiling points. Now, compared to other hydrocarbons and ethers of comparable molecular mass, aldehydes and ketones have a higher boiling point. And this is because of the weak molecular association because of dipole-dipole interactions. And we know that the carbon-oxygen bond has a dipole moment, and that makes the compounds have a weak molecular association. And this in turn is going to lead to a higher boiling point compared to ethers, hydrocarbons of comparable molecular mass. But they have a lesser boiling point compared to that of alcohols. And this is because in case of alcohols, we have hydrogen bonding, intermolecular hydrogen bonding, which are much stronger than dipole-dipole interactions. Next is miscibility with water. Now, lower members are miscible with water in all proportions because of the hydrogen bond formation with the water molecules. And when there is an increase in chain length, the alkyl group increases and the solubility is obviously going to decrease. And this is what we observe in almost all the cases. Next is solubility in organic solvents. Aldehydes and ketones are fairly soluble in various organic solvents. Odor, pungent odor for lower aldehydes. And when the size of the molecule increases, the odor actually becomes fragrant. For example, vanillin is one of the most common aldehydes. It's one of the most common flavors that we know in our daily lives, and that is actually a carbonyl compound. So Naturally occurring aldehydes and ketones are used for perfumes as well as flavoring agents. With that, we're done with the physical properties of carbonyl compounds. Chemical properties of alcohols, aldehydes and ketones. First of all, these are the various reactions we'll be learning for aldehydes and ketones. Nucleophilic addition reactions, reduction, oxidation, reaction due to alpha hydrogen, and other reactions which are, mentioned below. So first is the nucleophilic addition reaction. Let's look at the mechanism. Now, when you have the carbonyl carbon, as I told you when we talked about the nature of the carbonyl carbon, we know that it's electrophilic in nature. And this is because of the oxygen atom being more electronegative. So nucleophile is going to come and attack the carbonyl carbon, and this is going to shift the double bond towards the oxygen. So what happens is it is attacking the direction perpendicular to the sp2 orbital, and the carbon atom is going to get converted from an sp2 hybridized to an sp3 hybridized carbon atom, and this leads to formation of this tetrahedral intermediate. And after that, this can easily the O minus can easily capture a proton, and this leads to the formation of the neutral product. So what is happening? Nucleophile is attacking the electrophilic carbon atom, and the reason this is an electrophilic carbon atom is because of the electronegativity of the oxygen atom. So nucleophile is attacking at the perpendicular position, and the carbon atom is converted from an sp2 hybridized carbon to an sp3 hybridized carbon atom, and this leads to the formation of an alkoxide intermediate, and this alkoxide intermediate is tetrahedral, and it can easily capture a proton to become an electrically neutral compound. Next is reactivity. Now when we talk about aldehydes and ketones, as we know, the aldehydes have, in case of aldehydes, you'll have an alkyl group and a hydrogen atom, whereas in ketones, you'll have both alkyl groups. Now, there are two reasons why aldehydes are more reactive towards nucleophilic addition reaction than ketones. The first one is going to be steric reasons. Now, A and B. Now, if A and B are both alkyl groups, then obviously they will not. It'll make things difficult for the nucleophile to come and attack the carbonyl carbon. However, if one of them was a hydrogen atom, it's smaller compared to an alkyl group, obviously, then that decreases the steric hindrance to a great extent compared to that of ketones. And so it's easier for the nucleophile to attack when it's an aldehyde than when it is a ketone. The next is going to be electronic reasons. Now, in case of an aldehyde, you have a hydrogen and alkyl group, and in ketone, you have two alkyl groups. And the presence of these two alkyl groups is going to decrease the electrophilicity. And the reason this is the case is because alkyl groups are electron releasing in nature. So the electrophilic nature of the carbonyl carbon is going to decrease due to the presence of two alkyl groups. Whereas in case of aldehydes, you have an alkyl group and you have a hydrogen. So compared to ketones, we're talking about it in comparison to that of ketones. Obviously, the electrophilicity is not decreased as much as in aldehydes as it is in ketones. And that is why aldehydes are more reactive to nucleophilic addition reactions than ketones. Two reasons: steric and electronic reasons. Next, we're going to be talking about various examples of nucleophilic addition elimination reactions. The first one is addition of hydrogen cyanide, that is HCN. Aldehyde or ketone is going to react with HCN, and this leads to the formation of something called as a cyanohydrin. And cyanohydrin is actually a very useful synthetic intermediate. Now, when we are taking only HCN, the reaction is quite slow, and to avoid slow reactions is not going to be very helpful. So what we do is we add a base, and this base is going to convert the HCN to form the Cn minus. And Cn minus, that is a cyanide ion, is more reactive than the HCN itself, and that helps in the formation of the cyanohydrin. The second reaction is addition of sodium hydrogen sulfide. So aldehydes and ketones are reacting with NaHSO3 to lead to the formation of an addition product. Now, when in this reaction, we are getting a bisulfite addition compound, and this is the intermediate that we get. Now, when we talk about equilibrium, so it lies on the right for the aldehydes, and for ketones, it's going to be on the left. And this is because of steric reasons. So because of the steric reasons, the aldehydic products are, the equilibrium is going to be for the on the right, whereas for the ketones it's going to be on the left. Now this addition product which is formed is actually soluble in water, and it can be used, and when it's dissolved, when it is treated with dilute mineral acid or alkali, we get back the carbonyl compound, and this makes it a good method for the purification of aldehydes and separation of the aldehydes. So you have two ketones, and you have a ketone and an aldehyde. Because the equilibrium is on the left for ketone due to steric reasons, due to that, it will not undergo the reaction to an extent as the aldehyde would. And so this particular way is actually useful for the purification and the separation of aldehydes, or rather separation and purification of aldehydes. Next is addition of Grignard reagent. Now, this particular reaction was studied in chapter 11, that is alcohols, phenols, and ethers, and this was used for the synthesis of of alcohols from aldehydes and ketones. So here you have it consists of two steps. So nucleophilic addition of the Grignard reagent. So here the Grignard reagent is going to act as a nucleophile to form an adduct, and this adduct is going to undergo hydrolysis to give us an alcohol. And as we know, methanol is giving us a primary alcohol, aldehydes will give us secondary alcohols, and ketones will give us tertiary alcohols in this mechanism. In this method of preparation. Next is the addition of alcohols. Now, aldehyde, when it reacts with a monohydric alcohol, it forms an alkoxy alcohol. It is called as hemiacetal. Now, this hemiacetal is going to react with another molecule of the alcohol to give us acetal. So first, aldehyde reacts with the alcohol in the presence of HCl, trihydrochloric acid, to give us hemiacetal. This hemiacetal is reacting with another molecule of an alcohol to give us acetal. Similarly, ketones give us, on reaction with ethylene glycol, here you have two hydroxy groups. So it reacts with both of these to give us something called as ethylene glycol ketal. And the reason we have HCl gas is because it helps in protonation. And protonation basically means the addition of the hydrogen atom. And this increases the electrophilicity of the carbonyl carbon. So what happens is this protonates the oxygen atom to form OH, right? And this increases the electrophilicity of the carbon atom. Next, on hydrolysis with aqueous mineral acids, they form corresponding aldehydes and ketones. So when these react with aqueous mineral acids, they lead to the formation of aldehydes and ketones, corresponding aldehydes and ketones. The last one is the addition of ammonia and its derivatives. So here, the nucleophile is going to be the ammonia and their derivatives, and it adds to the carbonyl group. Now, it actually is a reversible reaction, as you can see with the double-headed arrows, because of the dehydration of the intermediate forms this particular compound. Now, the Z can be anything. It can be an alkyl group, an aryl group, an OH, and an H2, anything. And based on the kind of the reagent which is being used, various types of products are formed. The next one is reduction reactions. Aldehydes get reduced to alcohols, primary alcohols, whereas ketones get reduced to secondary alcohols. And I'm sorry, here it should have been reducing agent. So the reducing agent used are sodium borohydride or lithium aluminium hydride. The next one is reduction to hydrocarbons. Here you have two named reactions, Clemenson's and Wolff-Kishner reduction. So Clemenson's reduction involves the reaction with the zinc amalgam and concentrated hydrochloric acid. And this leads to the formation of an alkyl, the CH2 group. Whereas the Wolff-Kishner reduction, also notice both these reactions give us the same major product, right? But the other byproducts which are formed, in this case it's water, whereas here you have N2. But not only that, Wolff-Kishner consists of another step in between. So what happens is carbonyl compounds are reacting with hydrazine to give us a hydrazone. And this hydrazone is reacting with sodium or potassium hydroxide in high boiling point solvent like ethylene glycol. And when that happens, it is giving us a CH2 group and nitrogen gas. So Clemenson and Wolff-Kishner, both of these are quite similar. In both the cases, you have the major product as an alkene, the CH2 group, but the reagents used are different. In Clemenson, we have zinc amalgam and concentrated hydrochloric acid, whereas in case of Wolff-Kishner, we have a hydrazine reaction with hydrazine that gives us a hydrazone that followed by reaction with potassium hydroxide in the presence of ethylene glycol and heat gives us a CH2 group and nitrogen gas. The next reactions we are going to be learning about oxidations. Now, when aldehydes and ketones, obviously their reactivity is different. They obviously will oxidize to various extents. So when we talk about aldehydes, they undergo reaction in the presence of mild oxidizing agents as well. But ketones, they require strong conditions for them to undergo oxidation. So aldehydes on oxidation give us an acid. Whereas ketones require a high amount of energy because there is a cleavage of the carbon-carbon bond. And because of that, you have a mixture of acids with various number of carbon atoms. So common oxidizing agents that can be used are nitric acid, potassium permanganate, potassium bichromate, etc. But the mild oxidizing agents are where you can actually see the difference between aldehydes and ketones. So Tollens and Felling's reagent, both of these are very useful for us to distinguish between aldehydes and ketones. And as you would expect it to, aldehydes undergo reaction with the Tollens and Felling's reagent, but ketones do not undergo the reaction because they require vigorous conditions. So let's talk about Tollens reagent or Tollens test. So Tollens test is using Tollens reagent. It's going to be ammonical silver nitrate solution. So what happens is the aldehyde is warmed with this freshly prepared Tollens reagent, and you will see this beautiful silver mirror on the inside of the test tube. It's actually really pretty and it's quite reflective, and you can see yourself. I mean, you can see your face on that. So this particular reaction shows that you have an aldehydic group. And this takes place in an alkaline medium, and this leads to the oxidation to form the carboxylate anion. So you have the aldehyde undergoing oxidation to give us a carboxylate anion. Felling's test consists of two reagents, Felling's A and Felling's B. And Felling's A and Felling's B are mixed in equal amounts. Felling's A consists of aqueous copper sulfate, whereas Felling's B is alkaline sodium potassium tartarate, which is called as Rochelle salt. So what is going to happen over here is similar to the previous case. Here also aldehyde is heated with the mixture, and this gives us a brown precipitate. Now here also you have the same thing. You have the aldehyde undergoing oxidation to give us the carboxylate ion. But here you have a difference in terms of the kind of byproducts formed. Here you have Cu2O, H2O. Here it is silver because that was the silver mirror that you observed. Aromatic aldehydes, however, do not undergo Felling's test or reaction in the presence of Felling's reagent. Next is oxidation of methyl ketones by haloform reaction. So aldehydes and ketones with at least one methyl group react in the presence of sodium hypohalide to form sodium salt of carboxylic acid with one less carbon atom. So the methyl group is getting converted to give us haloform. So here, notice you have NaOX. This is giving us sodium salt of carboxylic acid. The methyl group is forming haloform. The methyl group is getting converted to haloform. But the double bonds which are present in the compound are not going to get affected by this reaction. Now, this iodoform reaction is actually used for the direction of various groups. Now, reaction due to alpha hydrogen. As I told you when we studied about aldehydes and ketones, the alpha hydrogen, alpha carbon is the one which is attached to the carbonyl carbon. And the hydrogen attached to the alpha carbon are called as alpha hydrogens. And this hydrogen atom is actually acidic in nature. And because of this acidic nature, it is going to undergo, carbonyl compounds are undergoing certain reactions. And this is over here. Okay, yeah. So the reason this is acidic is because the electron withdrawing effect of the carbonyl compound, carbonyl group, and the conjugate base is going to be resonance stabilized. So if this hydrogen atom is going to get removed, you have a negative charge, and that is resonance stabilized. And so this hydrogen atom is acidic. So there are two reactions we'll be learning about: aldol and cross aldol condensation. Aldol condensation is basically the aldehydes and ketones, they have at least one alpha hydrogen. They will undergo self-condensation. And this is going to take place in the presence of dilute sodium hydroxide or a dilute alkali. So there is something called as a beta hydroxyaldehyde which is formed, and this is called as an aldol. And aldols actually on heating eliminate the water molecule and lead to the formation of the aldol condensation product. So here you have the CH3CHO getting converted to 3-hydroxybutanal. Next, you have ketols formed when ketone is the reactant. And the reason we call it an aldol is because you have two functional groups, that's an aldehyde and an alcohol in the compound. Now, these aldols and ketols readily lose water to lead to the formation of the condensation product. And the name aldol is applicable to both ketones as well as aldehydes. And if a particular ketone and aldehyde does not contain a alpha hydrogen atom, it does not undergo aldol condensation. The next one is cross-aldol condensation. This takes place between two different aldehydes and ketones or ketones. So it gives us two. So here you have the reaction in the presence of sodium hydroxide, and this gives us 4 products. So this is again going to be based on the arrangement of the based on the reaction. And for you to understand this in detail, do check out my video on aldol and cross aldol condensation. And there's a separate playlist for all the named reactions that you learn in class 12. So if one of the reactants does not possess an alpha hydrogen, it does not self-condense, and so you will get one particular product as the major product. So for cross aldol and aldol, if you find it difficult, like I did when I was grade 12, I suggest you go check out the video that I uploaded about aldol and cross aldol, and that'll make things way easier than they are right now in your textbook. The last one is other reactions that we observe. So Cannizzaro reaction is observed by from aldehydes that don't have an alpha hydrogen. So they undergo disproportionation reaction. So disproportionation is when a particular substance undergo simultaneous oxidation and reduction to form two different products. So one molecule of aldehyde is going to get reduced to alcohol, while the other molecule of aldehyde is getting oxidized to form the salt of carboxylic acid. So here you have formaldehyde. It underwent oxidation, give us potassium formate, and it underwent reduction to give us methanol. And this reaction is with concentrated potassium hydroxide. Similarly, this case as well, you have benzaldehyde reacting with concentrated sodium hydroxide on heating, giving us the oxidized product, which is sodium benzoate, and the reduced product, benzyl alcohol. The last one is electrophilic substitution reaction. So the carbonyl group is actually meta-directing because it's deactivating in nature. So it forms a meta product. So here you have nitration reaction taking place, and the NO2 group gets added at the, or rather substituted at the meta position. With that, we're done with the various types of reactions that aldehydes and ketones undergo. We started with studying about nucleophilic addition reactions and then moved on to study about various reduction reactions. And remember, aldehydes, alcohols. This one, aldehydes undergo reaction to give us primary alcohols. Ketones, on the other hand, reduce to give us secondary alcohols. And then we moved on to study about oxidation. The reason these two oxidize to various extent is because in case of ketones, you have breakage of the carbon-carbon bond. And that's not the case in aldehydes. So aldehydes will get oxidized in the presence of mild oxidizing agents, and that is a way for us to identify the presence of an aldehyde or a ketone. So we can say, okay, this particular carbonyl compound consists of an aldehyde or a ketone, and that's actually quite helpful. Next is we studied about the oxidation of methyl ketone by haloform reactions, and the last one was studying and we studied about aldol and cross aldol condensation. I suggest, it's easy if you understand these reactions, but if you do not understand them, you don't actually have to memorize these products which are formed. So do not memorize, understand them, and then you'll be good to go. The last one was Cannizzaro and electrophilic substitution reaction. With that, we're done with the chemical properties of aldehydes and ketones. Aldehydes and ketones have various uses as written in this particular note, I guess. And like you can go through all the uses of aldehydes and ketones. One unique use I've always found for aldehydes and ketones is their odors and flavors. So they're used in perfumes, They use as flavoring agents, and I've always found that extremely fascinating. And the thing is, lower aldehydes are generally have very weird, I mean, bad odor, but like as you go up to higher aldehydes, they have very good and fruity and amazing odors. So just go through the various uses of aldehydes. Structure of carboxyl group. I think you figured out we're done with aldehydes, ketones, and basically aldehydes and ketones. And so we are going to be starting with carboxylic acids. So carboxylic acids have the functional group COOH attached to it. So in case of aldehydes and in case of aldehydes, you have H, right? That is replaced by an OH in a carboxylic acid. So in the structure of carboxylic group, you have the bonds of the carboxyl lying on the same plane, and they are going to be separated by 120 degrees. And this is similar to what we studied for a carbonyl carbon. So that's the same thing that is observed over here, right? So here you have this, and this, the bond's going to be lying in the same plane. And the carboxyl carbon is less electrophilic than carbonyl because of the various resonance structures that exist. Due to the various resonance structures, the carboxyl carbon is less electrophilic than carbonyl carbon. Nomenclature of carboxylic acids. First of all, common names. Common names, so carboxylic acid actually have been one of the oldest or earliest extracted organic compounds. And so their common names are the ones which they are most commonly known by. For example, acetic acid is ethanoic acid, but most likely you hear the word acetic acid and you know it's ethanoic acid. So they're more commonly referred to by their common names. So these names are going to be ending with oic acids, and they're derived from Latin or Greek names of the natural source. For example, formic acid is HCOOH, which was actually first obtained from red ants, and red ants are called as formica in Latin. Whereas acetic acid is extracted from vinegar, and in Latin, acetum means vinegar. Butyric acid is from rancid butter, and butyrum in Latin means butter. IUPAC names for these compounds, on the other hand, for aliphatic carboxylic acid, the alkane, the E of that is replaced by oic acid. And the carboxyl carbon is going to have number 1. Now, when there are more than one carboxylic group, they are numbered, leaving out the COOH, and they are numbered based on the Arabic numbers, and the number of COOH is denoted by dicarboxylic or tricarboxylic based on the number of COOH groups present. For example, there are no examples here. I'm so sorry. So they are denoted by the number of carboxylic acids, and the Arabic number is going to detect or denote the position of the COH. And COH is going to get the highest priority amongst all the functional groups that you learn. So that is going to be considered as the parent functional group. With that, we're done with the nomenclature of carboxylic acids. Here you have various examples of common names as well as the IUPAC names and structures of carboxylic acids. Methods of preparation of carboxylic acids. So there are 6 methods that we're going to be learning: from primary alcohols and aldehydes, from alkyl benzenes, from nitriles and amides, from Grignard reagent, from acyl halides and anhydrides, and from esters. So let's start. First is from primary alcohols and aldehydes. So primary alcohols are going to undergo oxidation to give us carboxylic acids. The oxidizing agents which can be used are potassium permanganate in neutral, acidic or alkaline media, potassium dichromate, chromium trioxide in acidic media, which is also called as Jones reagent. Now, aldehydes are also converted directly to carboxylic acids using mild oxidizing agents, and that's what we studied when we learned about oxidation reactions of aldehydes and ketones. Next is alkyl benzenes. Alkyl benzene is undergoing vigorous oxidation to give us aromatic carboxylic acid. So irrespective of the chain length, they're going to undergo oxidation to give us the aromatic acids, carboxylic acid. So the oxidizing agent used over here is chromic acid or acidic or alkaline potassium permanganate. Now, the primary and secondary alkyl groups are oxidized, but if this group was actually a tertiary alkyl group, it wouldn't have been affected. And these, the alkenes which have a specific substituent, can also undergo oxidation with this particular reaction. The next is from nitriles and amides. Nitriles on hydrolysis form amides, and this in the presence of H plus or OH minus as a catalyst undergo reaction to form acids. So here you have nitrile forming an amide, and this is reacting to give us an acid. And this mild reactions, actually, if the reaction conditions are mild, then the reaction stops at the amide stage itself. Next is from Grignard's reagent. So Grignard reagent is reacting with carbon dioxide in the presence of dry ether to give us the salt of carboxylic acid. And this on acidification with mineral acid gives us carboxylic acid. So it's undergoing acidification reaction. Here, Grignard reagent is actually prepared from alkyl halides, and this is used for the synthesis of an acid from an alkyl halide. The next reaction is from acyl halides and anhydrides. So acid chloride is going to undergo hydrolysis with water to give us carboxylic acid. And another one is by acid chlorides are also readily hydrolyzed with aqueous base to give us the carboxylate ion, which on acidification gives us carboxylic acids. So there are two reactions. First is hydrolysis with water. The second is hydrolysis with aqueous base. With aqueous base, it gives us a carboxylate ion, which on acidification is going to give us an acid. And the hydrides, on the other hand, are going to be hydrolyzed with water to give us the corresponding acid. So here you have benzoic anhydride. It's giving us 2 molecules of benzoic acid. Next is from ester. So ester undergoes acid hydrolysis to give us carboxylic acid. So here you have ethyl benzoate. It's undergoing hydrolysis to give us benzoic acid as well as ethanol. Now, in the presence, so this is acidic hydrolysis, right? When it's a basic hydrolysis, it's going to give us a carboxylate. And this on acidification is giving us carboxylic acid. So if you notice, there's some sort of similarity which we observe when we talk about acid halides and anhydrides and esters. That's because all of these reactions are actually hydrolysis reactions, first of all. Second of all, technically, these are all derivatives of a carboxylic acid. From carboxylic acid, you can synthesize an acid chloride. So because of that, all of these compounds on hydrolysis are giving us carboxylic acids. So with that, we're done with methods of preparation of carboxylic acid. We studied from primary alcohols and aldehydes, moved on to alkyl benzenes, nitriles and amines, from Grignard reagent, from acyl halides and anhydrides, and from esters. Physical properties of carboxylic acid. First, color. Aliphatic carboxylic acids having up to 9 carbon atoms are actually colorless in nature. In room temperature, aliphatic carboxylic acids with 9 carbon atoms are liquids, whereas higher carboxylic acids are actually wax-like solids. Boiling point. Now, carboxylic acids actually have a higher boiling point compared to all the other functional groups of comparable mass. And this is because of their intermolecular hydrogen bonding. And their intermolecular hydrogen bonding is so strong that even in vapor phase, the intermolecular hydrogen bonding exists. And because of that, carboxylic acids exist as dimers. Next is solubility in water. Now in so as we know, they have the ability to form hydrogen bonds. So the simple aliphatic carboxylic acids will be able to be dissolved in water. Now, when the number of carbon atoms is going to increase, then there will be a decrease in solubility because of the hydrophobic interactions. Benzoic acid, which is the simplest aromatic carboxylic acid, is insoluble in water. So this is the hydrogen bond with water molecules. The next is solubility in other solvents. So they are also soluble in solvents like benzene, ether, alcohol, and chloroform. So we learned about state, color, boiling point, which is higher compared to all the other functional groups of comparable molecular mass, like aldehydes, ketones, alcohols, like whichever you learned till now. And this is because of the presence of intermolecular hydrogen bonds. And they're so strong that even in gaseous phase or vapor phase, carboxylic acid exists as a dimer. Now they're soluble in water because of, again, the formation of hydrogen bonds. And this is again simply applicable to simple carboxylic acid. As the number of carbon atoms is going to increase, the solubility will decrease. With that, we're done with the physical properties of carboxylic acids. Chemical reactions of carboxylic acids. So these are the various reactions we'll be learning about. First is with there's a cleavage of the OH bond. The second involves the cleavage of COH bond. So there we talk about formation of anhydrides, esterification reactions, reaction with PCl5, PCl3, and SOCl2, reaction with ammonia. The last but one is reaction involving the COOH group, which is reduction and decarboxylation reactions. Last one in the lot is the substitution reaction in the hydrocarbon part. So you have halogenation and ring substitution. So let's begin. So reaction involving the cleavage of OH bond. Now acidity is the thing we're going to be talking about. Now, like alcohols, carboxylic acids undergo reaction with metals and alkali to lead to the formation of salt and hydrogen or water, depending upon the reactant. So here, if it's a sodium that is a metal, then the product is going to be hydrogen. When it's an alkali, it's going to be water. But alcohols do not undergo reaction with carbonates and hydrogen carbonates, but carboxylic acids do. And this leads to the formation of salt, carbon dioxide. And again, based on the reactant, you get water. Now, this reaction is actually quite useful for us to identify the presence of carboxylic group. Here you have a reaction, RCOOH, reacting with water to where there is going to be removal of this proton. The H is getting kicked out. And we have these resonance stabilized products. And this KEQ and KA are equilibrium constant and acid dissociation constant, which you've learned about in the chapter equilibrium. Now, when we talk about the strength of an acid, it is denoted by their pKa values. So pKa is minus log of the Ka value. So the logarithm of the acid dissociation constant, the negative logarithm of the acid dissociation constant is going to give us the pKa values. Now here I have a list of various acids with their pKa. You have -7 for hydrochloric acids, and acetic is 4.76. So obviously here the hydrochloric acid is the strongest, whereas acetic is the weakest in this set. So when you have the pKa value less than 1, it is a strong acid. Between 1 and 5, it's moderately strong. 5 and 15 is weak, and more than 15 is going to be extremely weak acid. Now, when we compare a carboxylic acid and phenol, their acidity is obviously going to be different. So first of all, their conjugate base, that in case of carboxylic acid, it's a carboxylate ion. Whereas in this case, it's a phenoxide ion. And the resonance structures in carboxylic acids, you have 2 equivalent resonance structures. And phenols, however, you have 2 non-equivalent resonance structures. And if you notice, in phenol, the negative charge is going to get delocalized between carbon atoms. Whereas in case of carboxylic acid, the negative charge is delocalized between the electronegative oxygen atom. And so for carboxylic acid, or carboxylate ion, that's the conjugate base of carboxylic acid, the resonance is more pronounced than that of a phenoxide ion. And that is why carboxylic acids are actually stronger acids than phenols. So first of all, we're talking about their conjugate base. For carboxylic acid, it's carboxylate ion. For phenol, it is phenoxide ion. Resonance structures, you have carboxylate, you have 2 resonance equivalent resonance structures, and the negative charge is getting delocalized between the electronegative oxygen atom. Whereas in case of phenoxide, you have the negative charge getting delocalized between the carbon atoms, which are not as electronegative as the oxygen atoms. So the effect of resonance in phenoxide is not as, it's not to a great extent as it is in the case of carboxylate, making carboxylic acid a stronger acid than phenol. Now, obviously, in the presence of various, groups, there's going to have effect on the reactivity, or rather the acidity of the acid. So electron withdrawing groups will increase the acidity because they will stabilize this carboxylate ion, whereas electron donating groups will decrease the acidity because they're destabilizing the carboxylate ion, which is the conjugate base. So these are the effects of phenol. Then you have phenyl group, iodine, bromine, chlorine, fluorine, cyanide, nitro, CF3. The below thing over here is the acid in their increasing order of acidity. So CF3COOH is the most acidic compared to CH3CH2COOH because you have The fluorines are actually going to help in increasing the acidity of the carboxylic acid because they are electron withdrawing in nature. Now, when you have phenyl or vinyl groups, we tend to assume that there'll be a decrease in acidity, but they actually increase the stability due to resonance. And this in turn makes the carboxyl atom more electronegative because, I'm sorry, the sp2 hybridized, this carbon atom is actually more electronegative than an alkyl carbon. And so it's more electronegative in nature and it tends to stabilize the carboxylate ion. In presence of electron withdrawing groups, the aromatic carboxylic acids, if there's an increase in acidity, electron releasing group will obviously decrease the acidity. With that, we're done with the acidity of carboxylic acids. Next is reactions involving cleavage of COH bond. First is the formation of anhydride. So carboxylic acid, when it's heated with the presence of mineral acids like sulfuric acid or P2O5, phosphorus pentoxide, it leads to the formation of a corresponding anhydride. Here, there is going to be elimination of two hydrogens and one oxygen, which is water. And that leads to the formation of an ethanoic anhydride. So there's a formation of a CO bond taking place. Next, esterification, one of the most commonly known reactions. Carboxylic acid is reacting with alcohols or phenols to give us an ester and water. And this reaction is known as esterification reaction. And the reaction takes place in the presence of mineral acid like concentrated sulfuric acid and excuse me, I'm so sorry, HCl gas, and this acts as a catalyst. So the mechanism consists of 5 steps. The first step is the protonation of the carboxyl oxygen. And what happens is this oxygen is going to get protonated. The reason this is getting protonated is to make sure that it activates it towards the nucleophilic addition reaction. So our OH is going to come attack the carboxyl carbon and this bond is going to shift upwards. That is the second step. So here you have a nucleophilic attack. Next, you have the proton transfer. So this hydrogen is going to move away and it's going to get attached to one of the OH groups. And this leads to the formation of a OH2 plus group. And OH2 is formed because it's a better leaving group than an OH. So that's the next step. After that, you have the elimination of the OH2 as water because there's a formation of a double bond. And the last step is the loss of proton to form an ester. So if you find it easy to learn the reaction like this, do that. Or if you find it easier to just do it step by step, I suggest you do it step by step and you get to the last product, that is the ester. Next is reaction with PCl5, PCl3 and SOCl2. This reaction is what we learned in alcohols, phenols, ethers. We also learned it for the synthesis of alkyl halides from alcohols. So here what happens is the OH of the COOH is going to get replaced by Cl. This is because the OH groups of a carboxylic acid is going to act as that of alcohol. So with PCl5, PCl3 and SOCl2 and similar to what was observed in alcohols, phenols, ethers, SOCl2 is preferred as the reactant because the byproducts SO2 and HCl are going to be gases, whereas in the other cases, these are not, and these won't escape into the air like these. So because of that, the SOCl2 is more preferred. Next is reaction with ammonia. So carboxylic acid is going to react with ammonia to form an ammonium salt, which on heating gives us an amide. And this amide is again a derivative of a carboxylic acid. And here you have the synthesis of phthalimide. If you remember, there's something called as Gabriel's phthalimide reaction, which you learned this year actually. Next is reactions involving the COOH group. Now it undergoes reduction to give us an alcohol. Reducing agent used is going to be lithium aluminium hydride, or it is better with diborane. This because diborane does not easily reduce functional groups like esters, nitro, halo, etc. Sodium borohydride does not reduce the carboxyl group. So the lithium aluminium hydride or diborane are the reducing agents used. Next is decarboxylation. Sodium salt of carboxylic acid, when on heating with soda lime, which consists of sodium hydroxide and calcium oxide in a ratio of 3:1, leads to the formation of a hydrocarbon and carbon dioxide. The same reaction can also be done with, so here you have Na2CO3 formed and RH, that is the hydrocarbon. Next, coal-based electrolysis involves the alkali metal salt of carboxylic acid undergoing electrolysis to give us hydrocarbons. And in this case, the hydrocarbon will consist of twice the number of carbon atoms of the alkyl group of the carboxylic acid. So it will form R as the product. That will be double the number of carbon atoms of the alkyl part of the carboxylic acid. The next one is substitution reactions in the hydrocarbon part. The reaction is halogenation, and it's also called as Helmholtz-Zelsky reaction. So when you have carboxylic acid with an alpha hydrogen, and it reacts with chlorine or bromine in the presence of small amount of red phosphorus, it leads to the formation of alpha halocarboxylic acid. So this is the alpha carbon, and so the hydrogen attached to it is the alpha hydrogen. So this hydrogen is going to get kicked out and the halogen atom is going to come in, and that's your alpha halocarboxylic acid. The reaction takes place in the presence of red phosphorus. The last reaction is the ring substitution. Now, aromatic carboxylic acid undergo electrophilic substitution, and obviously COH is ring deactivating, so it is going to be meta-directing in nature. But it does not undergo Friedel-Crafts reaction. This is because COH is ring deactivating. Secondly, AlCl3 does not want to, it acts as a catalyst in a Friedel-Crafts reaction, right? But the thing is, it acts as a Lewis base in the presence of COH, and it gets bound to the carboxylic acid, and so it does not help in the reaction of Friedel-Crafts reaction. So because of that, aromatic carboxylic acids do not undergo Friedel-Crafts reaction. So here you have nitration, you have nitro group at the meta position. Here you have bromination, and bromine is going to be meta position because of COH as meta-directing in nature. With that, we're done with the reactivity of carboxylic acids. Personally, honestly, I found the acidity reaction, acidity quite difficult. I don't know. I think the whole having it in the form of paragraphs, I found difficult. So instead, I put it in the form of points and tables as always. Hopefully, it is easy for you to learn and understand. First, understand all of this, and then automatically it will come to you during an exam. So with that, we're done with the chemical reactions of carboxylic acid. And yeah, oh, the named reaction in this case is the Helmholtz-Zelsky reaction. This is the last topic of carboxylic acids and the last topic of this chapter. These are various uses of carboxylic acids. They're given here, just go through them. With that, we're done with the chapter aldehydes, ketones, and carboxylic acids. I hope you understood all of them. Do not by heart all the reactions. It's a waste of time. Instead, understand them and try and learn them. Have such tables and, have a set, always have this on the top so that whenever you go through your notes, you look at it, you can recollect the reactions that are involved. And wherever possible, if you're able to remember the name, I suggest remember the name. That's one mistake I think I always managed to do when I was in class 12. I found it so difficult to study these reactions. There were so many of them, and honestly, it was quite difficult. And after I finished my master's in organic chemistry, I realized I might as well have learned the names instead of actually by hearting every single structure. From the names, you can automatically write the structure. So I suggest you do that. Have your own memory devices, and you'll find this chapter quite easy and fun. Also, for Aldol and Cross aldol condensation, I suggest you do check out my video on aldols and cross aldol condensation. It's much easier, and I explained it to a deeper extent in that video. I'll put I think I will put the video link in the description below as well as the banner above. And I hope you really enjoyed learning this with me as much as I enjoyed making these notes, to be honest, and teaching them to you. With that, we're done with aldehydes, ketones, and carboxylic acids, and all the best.